So welcome everyone to CC Colloquium for February 9th, 2022. We're pleased to have back Fran Bagenal as an encore performance. She was here, some of you may remember last semester, talking about some very interesting and important societal implications of science and the way we do science. And we wanted to have her back. We were hoping to have her back in person. Unfortunately, that didn't work out. So we'll get to that in just a minute. We're thrilled to have her in any capacity. Announcements. I think there's one announcement, which is Virtual Night Sky is tonight, and I think Rick wanted to say a few words about that.
Yeah, we I wanted to welcome everybody, just remind everybody we do that every other week. And tonight we have a special guest. Her name is Mary Wiatke, and she's from Santa Clara Pueblo. She's a Native American, and she also happens to be an archaeologist, and she works for the New Mexico State Cultural Preservation Office. And we're talking about the sun, we're talking about ritual, and we're talking about seasonal celebration and food. And so anyway, that's what it's about. If any of those things appeal to you, the food especially, then you should check out the Virtual Night Sky tonight.
Great. Any other announcements from anybody? Doesn't look like it. So I'm happy to turn it over to Lindy to introduce Fran.
Great. Well, Fran Bagenal was born and grew up in England and studied physics and geophysics at the University of Lancaster. In 1976, she moved to the US for graduate study at MIT, and her 1981 PhD thesis involved analysis of data of the Voyager plasma science experiment in Jupiter's gigantic magnetosphere. She postdoced at Imperial College London, but then moved to a faculty position at the University of Colorado in Boulder, where she has remained. She served on several mission teams and worked on data from many more, very broad mission experience. And she is world's expert on the mass and energy transport of the giant magnetospheres of Jupiter and Saturn. We are so pleased to have you with us today, Fran. Take it away.
Hostess has to disable sharing. Could you allow me to share, please? I'm sorry.
Got it. You're ready.
Okay, great. Got it. I just thought I would check. Okay, here we go. So I want to talk about the Juno mission to Jupiter. And although it's been there for quite some time, I'm going to start off at the very beginning and talk about the giant planet, because we need to start off with the basics here. Jupiter, of course, is about 11 times the size of the Earth, 318 times the mass, orbits of 5.2 AU. And this is the sort of map based from the Cassini observations of the belts and zones, the stripes, the big red spot, the sort of features you're used to. But I want to show this compared with Earth. And this is a movie of the Earth above, obviously, and Jupiter below. And you can see both Earth and Jupiter have belts and zones, but there are big differences, apart from the great red spot, of course, on Jupiter, that at Earth, there are fewer belts and zones. There are continents and oceans that sort of get in the way of the flows. And there are clouds with condensation and evaporation. And so there are some major differences, important similarities, but some important differences too. So what are we looking at? Well, when we look at Jupiter, we're looking at ammonia clouds, which is the top layer of the three layers of clouds. Ammonia at the top, ammonia hydrosulfide below, and then water under that. This is the idea of, this is from a textbook, and it shows you this is the idea of what we think is there. Now remember that the atmosphere is 99% hydrogen and helium. So these clouds and the ammonia and the water and so on are minor compounds, but they cause the clouds and the features that we see. Now, when we flew by with Galileo spacecraft, we sent a probe into the atmosphere, and we expected to go through these three layers of clouds and measure them. But what we actually saw when we sent the probe down in was a lack of clouds, particularly the water cloud. So what was going on? We think that the probe actually went into a gap between the belts and the zones, that sort of gray area up there. And this is a hotspot. So this is an infrared picture that was taken around the same time from the Earth. And you can see we probably went into a hot region where there was a lack of water. So The fact that we didn't see water is a problem. It's a major part of our understanding of how planets form. And so when you look at oxygen, third most abundant element in the universe, which obviously part of water, you would expect to see about a factor of 2 to 3 enhancement like these other elements we have. So what's going on here? Is this an atmospheric issue or is it bulk depletion? So this is a big issue for understanding how the gas giants formed, because we believe, standard picture, that the gas giants form when you have an ice core beyond, where ice freezes out away from the new sun, and then onto that gas, onto that core, in comes a hydrogen gas to form the gas giants. And so that was our main picture, or continues to be our main idea of how the gas giants form. And if we don't find the water, then this raises an issue with this theory of how the gas giants form. Now, we're going to go there with Juno, and the goal was to go look for the water and find out about the interior. And since we're flying over the poles, let's also try and understand the aurora, one of the things I'm interested in. So this is the Juno spacecraft, and I really want you to notice this person down here in the bottom left to give you scale for this vast spacecraft. This was a PI-led mission, the first officially competed New Frontiers mission after New Horizons was selected to go to Pluto. And so this is a billion-dollar mission. And you can see we have a bunch of instruments. This was a spinning spacecraft. We have the solar panels producing about 500 watts of power. And then the instruments we have out on the solar panel, we have the magnetometer at the end. Then we have particles instrument, Jade and Jedi. We have waves, electromagnetic waves, the radio and plasma waves will be measured over here on the bus. And then we have spectrometers. We have a microwave spectrometer, we have an infrared spectrometer, a UV spectrometer, and then we have a camera that we slapped on just to take a few pretty pictures, because you can't go to a planet without taking some pictures. Okay, and then we have a gravity science instrument. We'll talk more about the camera in a bit. So one of the things about Jupiter, we've known since the early 60s that there are trapped energetic particles trapped in the magnetic field of Jupiter. And this has been observed from Earth, looking at the radio emission. It wobbles up and down because of a 10-degree tilt of the magnetic field. But this is a nasty place to put a spacecraft, your electronics. And so we designed a mission that would fly over the poles from pole to pole, taking about 2 hours to go from pole to pole, moving at about 60 kilometers a second when we're in close. And then we would go underneath the radiation belts and above the clouds, go through that slot. Now, we planned originally about 32 orbits, and we knew that because of the oblateness, Jupiter spins every 10 hours, it's faster at the equator than the poles because of that spin, that the orbits will process down with going high, orbit 1 coming down, and eventually will cross through the radiation belts at some point. Now, what we wanted to understand, starting from the inside out, was how the interior structure is of Jupiter. So top right is a classic textbook view of Jupiter's interior, distinct layers of a core deep down inside, very dense, with the Earth for comparison, about 15 times the mass of the Earth. Then we have metallic hydrogen, liquid hydrogen, and then gaseous hydrogen in the outer layer. Now, to understand what's going on at Jupiter, you need to use the equation of state. That is the relationship between temperature, vertical scale here on this plot, and pressure here. And it's a little complicated. We don't really know and understand how this all works because of the high pressures. But we do know that at pressures of a few million bars, we are going to end up going into a plasma phase transition into metallic hydrogen. So that means then that the protons and the electrons can move separately, and you get a electrically conducting medium. Now, the pressure is important. You look at the high pressures at the center, 50 million bars, okay? What does that mean? Well, I did the calculation. That's 1,000 elephants standing on top of each other, with the bottom elephant standing on one leg, balancing on a stiletto heel. And if I were there, which I wish I was in Arizona, I could do the interpretive dance of this for you. But the point is that the pressure is very high. And you can imagine we can't get to such pressures in a lab on Earth. We have to use theoretical models for the equation of state. And so that is going to be important in trying to understand what's going on inside. Now, there are models, and before Juno, the idea was the range of the core masses would be somewhere from 5 to 15 Earth masses, and that the total amount of heavy elements would be somewhere between 5 and 40 times the mass of the Earth. So a big range depending on what kind of equation of state people use. And what we want to do is to measure Jupiter's gravity and get the distribution of mass inside. And we use a standard technique of Doppler shift. We have the spacecraft moving on an orbit. We measure small perturbations in that spacecraft motion, and that gives us the distribution of mass inside the object that it's orbiting. So that's very important for getting the mass distribution inside, the mapping out the gravity. Now, one uses the spherical harmonics, and this is a standard technique. And so you assume some functions given there on the left, illustrated on the right for the distribution of mass. And you have a bit of this and a bit of that, and a bit of the other, the different functions, those coefficients here, the CNM and the SNM are the different coefficients. And you try and take so much of each to map out the distribution of gravity around the planet. Now, for the Earth, this is done, the National Geospatial Intelligence Agency, no less, has given us this for the Earth at extraordinary high resolution. And you can see they don't just have 1 or 2 coefficients, they go up to several thousand coefficients, couple thousand coefficients. I'm not sure how much I really believe these numbers, but they claim, oops, sorry, let me just go back again, to develop the Earth's gravity to this level of high resolution. And we have a lot of spacecraft to make these measurements, but okay. At Jupiter, we have 3 parameters, and over 50 years, error bars have been getting smaller, but before Juno, we had a long way to go. Now, we also want to measure the magnetic field. And the way we do that, we fly over and map out the magnetic field. Because indeed, as I said, when you move inwards to higher pressure, you go from a molecular state of hydrogen to this plasma state. And so hydrogen becomes electrically conducting, first ingredient. You need some spin, second ingredient. And then you need an internal heat that drives the convection. And with those 3 components, you get the critical components for a magnetic dynamo. And since at Jupiter you have all 3 of these in abundance, we have a very strong dynamo inside Jupiter. Models here on the right give you a sense of what we think is going on, a rapidly rotating interior. But we don't really know exactly the size. And so somewhere between 80% to 95%, the radius of Jupiter is where we think the size of the dynamo is. Now, when we look again, we can use spherical harmonic analysis for the magnetic field, a different spherical harmonic analysis. And you can see that for the Earth, these green points show you that we've measured the Earth's dynamo to pretty high accuracy here out to something like the 14th component. For Jupiter, before Juno, we only had about 4 or 5. And so the idea is with Juno, we would go up to the 20 or more harmonic and measure the dynamo. Now, what's interesting is that once we start going to high degrees of complexity, which we have in fact been doing with Juno, we're going to get a better sense of the Jupiter's dynamo than we have of the Earth, because at Earth, we have a rock crust, and that rock crust has permanent magnetization from earlier dynamos, and the Earth's dynamo has been flipping, as you know, from back and forth over time. And so the crust has this complex magnetic field that hides the dynamo, the current dynamo that's inside. Whereas at Jupiter, with no rock crust, we're able to map the current dynamo in some detail, more so than the detail for the Earth. And this will be important for dynamo theory. Now, when we look at the outer layers of the atmosphere, we want to know what it's like underneath those ammonia clouds that we can see with visible light. And what happens is, if you go to infrared, the picture on the right, which is taken by the IOTF in Hawaii, you can see that you see between the ammonia clouds, there's bright red regions in infrared, deeper down, the heat coming out. And so as you look at infrared, you're looking deeper down through the clouds. And so here on the infrared, we can go down to a bar, a little below a bar, a few bars. Whereas if we want to look deeper through to the ammonia hydrosulfide water cloud and below, we need to use microwaves. And so the longer microwave wavelengths will penetrate deeper, and we'll see the heat coming from below. Jupiter actually emits 2.5 times more heat than it receives from the sun. And so it's a sort of glowing in the microwave region. And as the microwave, as we go over the planet, the microwave instrument will measure 6 different wavelengths, the emission that comes from below, and map out the microwave coming from the deep interior and give us a sense of the distribution of water, ammonia hydrosulfide, and then the outer layer of ammonia. So this is going to be key for penetrating below those top clouds and getting a sense of atmospheric structure beneath those clouds. Now, looking at the magnetic field penetrates out into space. And because the magnetic field is strong, many times that of Earth, then it extends a long way out into the solar wind. In fact, if you compare it with Earth, all of Earth's magnetosphere would fit within the planet Jupiter. And so Jupiter's magnetosphere extends for out to 60 to 100 times the size of the planet, and then extends all the way out past the orbit of Saturn downstream. We discovered that with Voyager. The planet rotates every 10 hours, and in fact, the whole of the magnetosphere rotates, is coupled to the planet, as I'll be talking about later. And Io, the innermost moon, Galilean moon, Io, Europa Ganymede Callisto, Io, that volcanic moon, is the source of most of the material, the sulfur and oxygen ions and electrons that populate this vast region. Now, we've explored this magnetosphere with many satellites, but always in the equator, and Juno is the first to go over the poles. Now, we've known about Io's role, the peculiar role of Io triggering radio emissions since the 60s. And there were ideas about conducting moon moving through a magnetic field, driving electrical currents and so on. But it was Voyager when we actually went there and measured and got to see what this moon was indeed doing. It generates a ton a second of material, it spews out, fills up this volume. Now here's this picture on the right is a Galileo image, and you can see white sulfur dioxide frost that comes out of these big plumes, and the yellow is sulfur. Now New Horizons, on its way to Pluto, measured this erupting plume, Tvashtar as it's called, and that is sulfur dioxide being spewed out to make an atmosphere, but also escaping from the planet. And to give you a sense of the volcanic activity, this is from Juno's GIRAM instrument, infrared, and you can really see that there are a couple hundred volcanoes erupting at any one time. This is by far the most volcanic object in our solar system. So ejecting a ton a second of gases that become ionized, form a big donut, a big torus of glowing clouds emitting in the UV and visible. And then we have a 1 million amp electrical current that couples between Io and Jupiter, generating aurora where those flux tubes hit the planet Jupiter. So all of this we knew as we sent Juno out there, that we hope to observe the magnetic fields, the electric fields, look at the aurora with UV and infrared, and then measure the charged particles with the JADE and JEDI instruments. So this is a comprehensive way of looking for the first time flying over the poles. So here I was allowed to go down to Lockheed Martin in Denver, go in and watch them making this great big spacecraft. There's a really cool movie actually you can watch online of the making of this spacecraft, a sort of time-lapse image. It's really cool. And you can see the behind my head is one of the microwave receivers that is used. And all of the electronics is put in a box here to try and keep it safe. So then here are the panels, the solar panels, and you can see the scale of this. You have the radio antenna that's communicating with Earth and used for gravity science. This is a big spacecraft. Now we put the spacecraft, shipped it to the Cape, put it on top of a rocket, slapped on some stickers, took a selfie, got ready for launch on the 5th of August, 2011. And when it was successfully launched, we then went out, but we didn't have enough oomph to get all the way out to Jupiter. So we had to go back, do an Earth flyby, and then get out to Jupiter, arriving on, so technically in universal time, it was the 5th of July, but of course in JPL, it was the 4th of July, and we celebrated accordingly. So it approached the planet, then went into orbit, and we went into these 53-day orbits, going all the way out to 100 RJ. These extensive was passing very close, and we've now done 39 orbits, the last one being last month, the 39th orbit like this. And what have we learned? Okay, so let me go through some of the things that we've learned. With the magnetic field, one of the great things, we've mapped it out and we found that it's pretty asymmetric between the north and the south. And you can see there's a bit of an anomaly here, some sort of blip in the equator. It doesn't look very dipolar, does it? And if you map this out and make this model of this, you can see you have a north pole, a south pole, the field going out of the north into the south. And then we have this rather anomalous feature, which is in fact this region here. You can see this, what we call the blue spot. Some people do, I don't like that name, but anyway. This is much like the Earth's South Atlantic anomaly on the Earth's magnetic field, where we have a weak field region over South America. And that's where there's enhanced radiation. And actually, that's where Hubble has to be careful going through this region, not to have additional extra radiation. So this is not unlike the Earth, that the Jupiter has an anomalous region. So when we look at the detail in the magnetic field, the more orbits we get, the more detail we get. So now on the left, you can see we're beginning to get up to, we were hoping for an N max of 20. We're now going out towards 20 few and multiple passes, and you can see we're getting much more detail as you make more passes. And we hope to get more detail after this, and then we hope to sort of maybe see if there's a temporal variation over the 5 to 8 years that we observe. When we look at gravity, we're also getting more detail. And that's telling us more about the distribution of mass inside. And what we're learning is very interesting. So we thought, and the textbook picture has very simple layers. What we're learning is that this core, where we think all the heavy elements are, onto which the hydrogen came in, what we're thinking here is that this inner region is more spread out. It's the heavy elements are not confined to a small inner layer, but are in fact mixed up out to about 40% of the radius. We're also learning that the helium rains out, doesn't dissolve in the hydrogen. So yes, it does not dissolve in the hydrogen. It tends to sort of separate out, like oil and vinegar in vinaigrette, if you like. They separate over time. So helium and hydrogen tend to separate out. And then we have a metallic region here, the metallic mantle where the dynamo is produced. And then we have this mixture of heavy elements mixed in with hydrogen and helium in this diluted core. So if we look at what the distribution is and compare it with various equations of state, there are various models now with a dilute core spreading out. Instead of having, this is density on the left, fraction of the radius along the x-axis, and you can see enhanced heavy elements going out some way. And so there's a lot of work happening with combining various equations of state, theoretical equations of state, and mixing out the heavy elements. And, you know, there are many speculations about why and how this happens. Could it be a part of the formation process? So you had some mixing of hydrogen in with those heavy elements? Or is it that you had a separate heavy element core, and then once the hydrogen came in, there was a mixing up of that heavy element core with the hydrogen? Or also speculated that maybe there was an impact and that led to more mixing of this core. So lots of ideas right now, and very interesting work going on, trying to work out what's going on using the constraints from Juno. So now if we move out from that deep interior and think about the atmosphere, what are we seeing? So we're combining gravity data, microwave, infrared, and visible observations to try and understand the atmospheric circulation. Now, we've known for some time, observing from the Earth with telescopes, the east and west belts and zones, and we can see that, but we want to look deeper and understand what it's like deeper down. So this is the sort of wind speeds that we've measured, similar to those observed by Voyager. So this is not particularly new. You can see there's more moving to the right than to the left. And then with the GRAM's microwave instrument, really beautiful mapping out of the heat coming from the interior, and then the colder, darker regions are the higher up ammonia clouds above. You can see the great red spot with the heat coming around the edges there. So this is microwave, sorry, this is infrared. This is infrared, micron. Now let's look at microwave with the microwave instrument. You can see now we look deeper, and what we see is this. So this is orbit by orbit. We have multiple maps, and you can see there's slight differences between them. But what's interesting is there's definitely an enhanced amount of ammonia near the equator. So this is latitude with the equator at the center, latitude in either direction out to 40 degrees, plus or minus, and then pressure in bars. So one bar up here is the pressure in the Earth's atmosphere, what we're breathing. And so you can see we're going down to over 100 bars, 200-300 bars, and you can see the amount of ammonia is not uniform. It's distributed with this equatorial enhancement, and is varying on pass by pass. So this is telling us something about the distribution of ammonia inside, and actually is making it harder, this non-uniform distribution, to work out the amount of water, which you will remember was one of the main goals of this mission. So what we're seeing is that this distribution of ammonia is consistent with some very deep belts and zones, convective cyclone, anticyclone belts that are going east and west winds, and different depths. And so this is the picture that we're beginning to develop of what's going on. So if you look on the left, we have the belts and zones, a limited number of them for the Earth. And these tend to be, you can see they look rather flat rather than round. And that's because the thinness of the Earth's atmosphere and the limited number of belts and zones. So the Earth, remember, takes 24 hours to spin once, whereas Jupiter spins every 10 hours. And of course, Jupiter is 10 times bigger as well. So a lot of angular momentum at Jupiter, and that enhancement of rotation, very dominated on the flow, leads to more cells and the fact that they're more round. And there's no friction with continents and oceans underneath. We don't really know what causes the bottom layer of these belts and zones, but it's clearly some similarities, but substantial differences. So the question of how deep do they go, what happens at the bottom, is there interaction with the dynamo, is there something that causes the sort of the end of that separation of the deeper flows associated with the dynamo with the outer layers, and that's what people are thinking about. So I want to get to that camera. And being a particles and fields person, I'm a little bit snooty about cameras because, you know, they can just take over the mission. You know, oh, we got to go look over here. Oh, we have to go look over there. And everybody else has to bow down to the cameras, and the cameras are the, you know, everybody. And so we slapped on this camera just to take some publicity pictures. And it was kind of cool. We turned it into this citizen science project. And, you know, I am a complete convert. I think this is absolutely fantastic. Not only the concept of being a citizen science, but also the pictures that it's been taking. So let me show you a bit. We started off with having people put votes on what they wanted to take pictures of and get involved in discussions and planning. But the most important thing is the image processing, because these images are all made available pretty much immediately to the public online. And you can go to the Juno Cam website and see them and download them. And these are ones that have been processed very limited amount to make them look like true color, what we think is true color. And so you can see they're a little bland. Okay, now remember, we're going a lot closer to Jupiter than any other spacecraft has, and so we're getting really close-up views. And now what happens is, if you crank up the color contrast, you can begin to see some things. So these are the sort of images we've been getting. And this is where you really crank up the color contrast, okay, and you really get to see a lot more stuff. People can do what they want, it's okay. And or you take the contrast, you know, you can play around with that. You know, if you've played with Photoshop or any of these techniques, you can do lots of things. But it's interesting. You see things, right? When you really play with those images, and that's okay, because these belong to everybody. You know, every taxpayer is paid for these images, and they're entitled to have them, play with them, and put them up. And indeed, they do art, all sorts of cool art. And we've been posting this art. So this is fun. This is great. I'm a complete convert. I'm going to go through and show you some of these cool pictures that people have been looking at. And you can see the quantity of turbulence in this atmosphere is amazing. And you can see a range of different colors. They're probably exaggerated colors, but that's okay. As long as you realize that. You're seeing structure, you're seeing processes which are really cool. Okay, this is less contrast, but also very aesthetic. And you can see there's clearly a huge amount of turbulence in this atmosphere associated with the belts and zones, interactions between east-west winds, producing cyclones, anticyclones, and so on. One of the interesting things that these high resolution close-up pictures have produced is you can see these sort of little white little bits, and these or what we call pop-up clouds, for want of a better term. They seem to be as if ammonia has been pushed up and then condensed on top. And you can see this up here. And I took this picture on my way in the days when I flew out to Washington for meetings and come back again, but this is taken near Denver. And you can see these are Earth water clouds, but you can get a sense of this idea of a pop-up cloud. And so maybe this is what we're seeing, these fresh clouds that pop up here. And especially when you're near the terminator, you can see the structure and how they stick up. This is one of my favorites, the owly eyes. Isn't this cool? I just love some of the pictures and you know, humans have been looking at the sky and seeing things in clouds, right? And thinking they're seeing a cow or a human or a bird or whatever in the clouds. And here's Danny the dolphin. Isn't this cool? And he's being chased by a dragon. And oh, look at the pelican over here. Isn't this cool? Anyway, of course, the next orbit, it was gone, but these are fun things. So mixture of science and art. Here's the bowling ball. Look at those turbulent structures. Isn't that cool? All sorts of really neat stuff. Now, of course, people are doing science as well and not just going ooh, ah at the clouds. This is the first time we've flown over Jupiter poles. And you can see in the visible light, you have this around the equatorial region, the clouds are sort of brownish. We think that coloring is associated with radiolysis products of interaction of sunlight with ammonia and hydrocarbons, minor species in the atmosphere, but make these colored clouds. We can talk more about that later if you want. The blue is like the blue of our atmosphere. It's really scattering by the molecules in the atmosphere. But you can see now for the first time, because whenever we've looked before, we've been at the equator, not being able to see the poles. Juno is the first thing that's flying over the poles, and you can see these cyclones. Now, on the right, we look at the GRAM in images, and these are in the infrared, and you can see multiple cyclones here. And in the north, we have 8, in the south, we have 5. Now, this is interesting that these are persisted. And here we have a bunch, this is a movie showing a bunch of different ones. And the number of cyclones has remained the same in the north and the south. Now, sometimes a little cyclone sort of wants to come in and tries to push things around. You can see here, yeah, you can see where sometimes they come and they either get spat out again or they get absorbed in one of these larger cyclones. And so now we're thinking about why is it that we have a stable structure for over 5 years now with 5 cyclones in the north and in the south and 8 in the north. So this is interesting observations that we've been observing over time and trying to understand what's going on. Now, this past AGU, there was a very nice presentation by Leah Siegelman. She's an oceanographer. And when she started to see these clouds at Jupiter, she said, you know, these are just like the dynamics that I see in the oceans. Now, the picture on the left is of, it's colored by algae in the ocean. And if you, again, crank up the contrast, in the Baltic Sea, you can see this sort of structures, these sort of turbulence in the flow. And on the right, we've taken a Jupiter picture and colored it so they look similar. And you can see the role of turbulence. And now we're beginning to think that Jupiter's dynamics of atmospheric dynamics are probably more similar to the Earth's ocean dynamics, where rotation is important, turbulence is important, convection is important, and maybe certainly there's no friction with a surface, ground like there is at Earth, and the role of moist convection is less important. So condensation and evaporation are less important. So it's interesting that it took an oceanographer to come in and start talking with us for us to begin to understand what we think may be happening in the dynamics at Jupiter. And here is another example where this is the ocean in the Norwegian Sea. You can see these two vortices, a pair, a dipole, and then they've changed the color and superimposed Jupiter, and this Jupiter one's very similar. Now, I agree, just because they look similar doesn't mean the physics is the same, but there's some argument that the fluid dynamicists are now making that the Earth's ocean gyres are actually pretty similar to Jupiter's atmospheric dynamics, and indeed some of the Jovian dynamicists have been saying this for some time, and that we should think about ocean dynamics as the fluid dynamics that's similar to the atmospheric dynamics at Jupiter. So let's talk about the Great Red Spot. What is going on with the Great Red Spot? This is a Hubble picture, and but we need to go back and think about the history of the Great Red Spot. So there's some question whether Galileo actually saw it, but certainly Cassini saw it. He had a bigger telescope. He was at the Observatoire de Paris and was observing the Great Red Spot, monitoring it and looking at it. And then since then, it's actually disappeared for a while. We didn't see it. And that may have been just observing, got busy looking at other things. But since the mid 1600s, the spot has been observed and monitored ever since. And amateur astronomers, professional astronomers have been looking at Jupiter and mapping it out and recording it ever since. And indeed, here are some drawings from 1906 through to 1919. Here are a bunch of ones showing variations over time. But Voyager flew by in 1979 and made this movie. Color's a bit off, but you get the idea. Dynamics, it's about twice the size of the Earth, rotates every 6 days or so, and we were able to map these dynamics of what's going on. And for scale, let me also put in Katrina here, just to give you a sense of the size. So obviously this is a vast storm. So what did Juno see? Aha! I guess this is art. You might call it art. Maybe it's science fiction art. Okay, cool. Never mind. This was fun. Okay, what did it really see? What it really saw was that the Great Red Spot shrinking, more like 1.5 times the size, and more round and darker at the center. And we begin to see the edges and what's going on at the edges. And in fact, there's a lot of turbulence where the interaction of the Great Red Spot with the surrounding material. This is a rather beautiful picture showing you the turbulence sort of downstream. So the flow is going around, and this is sort of a downstream turbulence that's generated. Now, when we look at the microwaves again, we can look deeper. And what we're seeing is the Great Red Spot is quite deep, goes down to at least 300 kilometers. Some people say it may go down as far as 1,000 kilometers, a long way down into the atmosphere. But we have to think about what this means in terms of actual scale. So if you take the Voyager 2 Earth size and you work out the aspect ratio, if it's 300 kilometers deep, the aspect ratio is tiny, right? And then even if it's 1,000 kilometers, it's still, you know, more of a pancake than anything else. And if you look at on the scale of Jupiter itself, it's very much a surface feature. So although there's a temptation to think that this penetrates deep into the Dynamo region or something, oh no, it's very much just on the surface. So what has been happening with time? Well, Amy Simon has been putting together a catalog of what's happened over centuries, and you can see the Great Red Spot drifts around in longitude, but more importantly, I want to show you how its size has changed. And I'm going to put an Earth up here for scale. And so it's changed in scale from about 4 Earth 4 Earths to 2, and you can see over time it's been shrinking. So Voyager was here where it was about 2, and now if we look with Hubble pictures, well, okay, we can extrapolate, anybody can draw a line through, we keep that line going. What is happening? Well, you know, it will disappear at the end of the century, or maybe it will grow back. We'll see. Well, next generation will be able to observe this. This is a cool thing. It's an amazing phenomena of our, probably the most, certainly the biggest and one of the more important phenomena, atmospheric phenomena of our solar system. Let's watch it and see what happens. Okay, so the last topic I want to wrap up on is the magnetosphere and the aurora. Hubble has been observing the aurora for some time. This is where we have tens of keV electrons bombarding the atmosphere, making the hydrogen glow. And you see these emissions, and we've been observing them, and we now know, have a good sense of what's happening. These spots are associated with the moons Io, Europa, and Ganymede. I'll talk a little bit more about that in a bit. We have a main auroral region, which has 2 zones, zone 1 and zone 2. We'll maybe mention a bit more about that. We have polar aurora, and then we have more fuzzy diffuse aurora around that. Now, of course, what we wanted to do is compare with theories at Earth, and we think there are some similarities, but there are also many differences. One thing to look at is north and south, and here we see what is the effect of that magnetic anomaly. It causes the north one to look more like a kidney bean, while the south one is quite round. They're fairly consistent in size and don't vary a whole lot, unlike the Earth's aurora, which does vary a lot with solar wind conditions varying. It's much more static at Jupiter, though there is variability, probably not related to the solar wind. Now here you can see the UV observations at the top right, and the different colors there mean the different energies of the electrons bombarding the atmosphere. But when we look at the infrared from GRAM and the UV from UVS, you can see there's sort of some differences in structure, which is really telling us about the process of the bombardment of electrons into the atmosphere. So a bit about the atmospheric chemistry, a bit about the atmospheric structure, but also about the energy of the particles that are coming in and bombarding the atmosphere. And what we're learning is that, that we have a whole variety of processes. Some of them are similar to that of the Earth. We know that there are electrical currents that come in at the polar region, come out at the closer towards the equator. And this couples the rotation of the planet, of Jupiter, to the plasma sheet, the plasma that's produced by Io, this volume out there. So it's a way in which momentum is transferred from Jupiter to the plasma sheet. Now, we had some idea of what we would expect, but what we're learning with Juno is it's much more variable than we thought. When we look at the electrical currents, they're called Birkeland Currents after the Norwegian Birkeland who discovered them on Earth. But what we find is that when we fly through here with Juno and make these measurements of the electrical currents, the field perturbations, what we find is that they're much more patchy and much less consistent. They're surprisingly weak and variable, which was a surprise to us. We thought it would be a steady current that's just constantly flowing like a wire, but that's not the case. Similarly, what we're seeing is the system seems to be quasi-stable. That is, it's varying on short timescales as we fly through, that there are strong coupling currents, but they seem to be so strong that they go unstable. We do see electrostatic potentials, the electrostatic voltages, like a battery, if you like, that accelerate particles. But again, they seem to come and go. But we do see a lot of turbulence, evidence of that turbulence in the particle distributions and in waves and so on. So it's you know, surprise, surprise, you get in close, you look close, you see a lot more structure. Now, we did fly through the EO flux tube. That is the flux tube, the magnetic flux tube that connects EO to the planet where the aurora is at the foot. We mapped out that flux tube. It seems to go almost around all the way. This is looking at the North Pole, all the way around. We see spots, we see structures. And we have a sense now that EO generates these alphane wings, alphane disturbance. It's a wave that moves along the field, bounces back and forth as the plasma moves past EO. We also accelerate electrons. They produce beams that go from north hemisphere to south hemisphere. And these produce aurora that's been observed with Hubble and with Juno. And when we map out these waves and where we expect them, the beams to hit and produce aurora, the predictions seem to work quite well when compared with the observations made by Hubble and by Juno. So that we've now beginning to understand. Now, the next phase of the mission, we've just been selected for extended mission, so we hope to keep going to 2025, maybe as many as 75 orbits. And what will happen here is the orbit will begin to process downwards, and we will begin to cross. We've already done a flyby of Ganymede. We'll begin to do a flyby of Europa, eventually of Io. We'll pass close to the Gossamer rings. And we hope to survive through to 2025. That's the plan of what we will see. And we'll measure the plasma that's produced by Io and spreads out past Europa and out to Ganymede. So last summer, we flew past Ganymede. This is a fabulous picture that we took. We actually have really pretty high resolution observations of Ganymede taken by the camera. And we also, Ganymede is the only moon that has its own magnetic field. So it's a magnetosphere within a magnetosphere. This was been known from the Galileo mission, but Juno flew past, and we're having a great time having good arguments about what we're seeing with the Juno flyby and what it all means. We had an hour-long argument this morning between the particle instruments and the UV auroral instruments, trying to understand what's going on there at Ganymede. And so this will be, stay tuned for what we observed with Juno. So what we're doing with Juno is we're flying past Jupiter. We're looking at the clouds on the outside. We're penetrating deep and trying to understand what's inside. We're flying over the aurora, measuring the charged particles that produce the aurora and looking at the auroral measurements. We're penetrating deep with gravity, with microwaves, with the magnetic field. And all I can say is we know that this cartoon picture is now wrong, and it's a lot less fuzzy. It's lot fuzzier, a lot less linear in structure inside. And with that, I'll thank you very much and take your questions.
Great, thank you. That was some spectacular science and imagery. That was really cool. Questions, please put them in the Q&A. And I have to say as a, oh, I'm blurry now. What's trying to put that? I have to say as a low temperature geochemist interested in oceans and atmospheres and stuff like that, the parallels with the ocean turbulence were really amazing. That was really cool.
That's some new results. Really interesting, isn't it? Yeah.
Yeah. So questions for Fran?
Sorry, it was quite a blast.
Yeah, but it was, no, I'm a little surprised. Oh, here's one. Oh, can you show the website for the images one more time? I apologize, I did not get it written down fast enough.
Oh, okay. Okay, you can just Google JunoCam, but I will share my screen and go back to that. There we are.
JunoCam. So here's a question. I was curious about the circumpolar cyclones. Have any hypotheses been proposed for their regularity?
Yes. So if you need a combination of rotation and this turbulence and some driving from inside, but particularly it's the convection that's important. Now, I'm not a fluid dynamicist, but I think let me stop sharing and then we can talk. I'm not a fluid dynamicist, but you know that how fluid dynamicists come up with these non-dimensional numbers that are ratios of different factors, okay? And what I've seen in their presentations is that if you take the rotation rate of Jupiter and you take the gravity, which gives you the scale height, the thickness of the atmosphere, and you take the size of the planet and you take the convection that's happening in those belts and zones, and then you end up with a criterion that gives you the instability that produces these set number of cyclones. Now, the difference between the north and the south is probably because you've got slightly different winds in the north and the south, but the difference between 8 and 5 is not enormous. But at Saturn, of course, you don't have these polar cyclones, you have a hexagon, right? Now, the big difference between Saturn and Jupiter is that it's a factor of 3 in mass, that Saturn is 3 times lighter, or Jupiter is 3 times heavier. And so the scale height, the gravity is stronger at Jupiter, so you have a smaller scale height. And so you end up getting the instability that produces cyclones at Jupiter, instability that produces a hexagon at Saturn. Now, there's a little bit of arm waving there, but the fluid dynamicists are beginning to churn out their non-dimensional numbers and say, oh, this blah blah number is this over here and it's that over there. They're converging on the idea of explaining it, but it's pretty cool that these are staying pretty stable over 5 years.
Okay, there are a bunch of questions now. Why do you think there's a possible impact theory for the heavy element core and hydrogen mixing? You mentioned impact as a possibility.
Because there's a whole community of people who just love impacts, you know. I don't know. It's just one way you can stir things up is to have an impact, you know, and people want to have impacts. You know, it's like, why is Uranus tipped on its side? Oh, must be an impact. Yeah. I'm
right.
Sorry, I'm being a bit facetious here. I don't think we know or understand at all. But
right. All right. So Dan Shim asks, he says, hydrogen is very reactive and a strong reductant. Hydrogen should undergo changes from gas to liquid to supercritical fluid with depth in Jupiter. So the chemical behavior of hydrogen should change with pressure. Are there considerations about this aspect of the interpretation of the Juno data?
Absolutely. I'm sure that the people who are doing this gravity, and they're not just looking at the deep layers with the gravity, they're also looking at the outer layers and trying to work out what's going on. So people like David Stevenson at Caltech, who's been thinking about this for a long time, absolutely, they're using the best equation of state that they can find. And I know that the Berkeley group are working hard on coming up with better equations of state, of how to describe these things. We're probably not going to get all that much better measurements, though there are some measurements happening, I believe, at national labs like Lawrence Livermore. They're trying to make measurements of high pressure hydrogen, but those things are indeed absolutely being included.
Okay. Are there any signs the magnetic field strength or structure changing over time?
Yes. So yes, there are claims. Kimmy Moore, who was at Harvard, is now at Caltech, has been making some claims. She's been analyzing the data, and there is some possibility that that blue spot, I hate to use the phrase blue spot because it's purely a choice of color contouring, what color you choose to contour your magnetic field. It's not blue the way the red spot is red. If you really went and looked at it with your eyes, the red spot would be red, but if you look at the magnetic field perturbation, it would not look blue. Sorry. Anyway, she's claiming that this anomaly is varying with time. And certainly as we get higher resolution measurements over the next few orbits, we will be able to measure perturbations in the anomaly. I think that will be important. We probably won't be able to make a prediction of when Jupiter's field will switch, the way the Earth switches every, I don't know, 200 million years or some large number, 200,000 years, 200,000 years. I can't remember the number. Maybe somebody knows. But with Jupiter, it could be a long time before it switches.
Someone asked, I thought I heard hydrogen plasma mentioned, but didn't catch where in the atmosphere this occurs. Did I hear this right? It seems surprising.
There is, okay, so there's deep plasma, hydrogen plasma in the interior, right? So it's metallic hydrogen, and that's where the dynamo is produced. So whether you call it a plasma or whether you call it a metallic, you know, I'm not a solid state physicist to say that, but there is hydrogen plasma in the ionosphere. And so we have protons and electrons, and they in fact do escape, and they form about 10% of the plasma out in the magnetosphere, with EOs, sulfur and oxygen ions and electrons forming the rest. Yeah.
All right, in the interest of time, we should wrap up. Just one exit question, a burning question here somebody has. Do you have a favorite football club in the European Premier League?
I've lived in America longer than I lived in England, and I'm not going to touch that question with a barge pole.
I had a feeling that would be your answer. It was a good question to end with. So great. So thank you very much, Fran. It was great to have you here. We'll get you here in person eventually again. And
I hope so.
and that was really spectacular.
Great questions. Thank you very much. Bye.
Thank you. Thanks, everyone.
Okay, thanks, Ariel. I'll see you next week in person, I think.
Yes, next week we'll be in person. That's the plan.
See you
Okay,
later.
Thanks, Rick.
all right, I'll see you in a bit, Rick.
Okay, bye-bye.